Hello, everybody. Welcome to this summary sessions of class 12th for your board examinations. I am your teacher, Dr. 𝐒𝐿𝐃𝐈𝐀, to help you excel in your board examination, which are going to come very soon, guys. So today's topic is electrochemistry, and we will be discussing inside out all about electrochemistry, how and why this chapter is included in class 12th grade curriculum, as well as what are the importance of this chapter in our daily life examples, right? And this chapter, I can tell you, is of immense importance according to two perspectives. The first one, for the exam point of view, they ask you lots of questions from this chapter. The other chapters, they may skip asking questions, but from this particular chapter, they will for sure ask at least one or maybe two questions. In our daily life, all around, we see that we use things to power up, things to work for you, and they all are under the electrical current influence. For example, my watch. It's working because of I am using electrochemistry in its behind of this machinery that I'm using in my watch. What do we actually use? We use battery, we use cell. What is cell and what is battery? All those differences also we are going to find out in today's session. How they are made, what are the components, every single thing in detail we are going to study, so that you bring your best in your board examination. Let's start, everybody. Okay. So these are the few components we will be discussing in this series today. First of all, I will give a quick round of introduction of what is this chapter all about, what do we study here, and the important points. For example, the electrode potential, which is of very carefully done and to be understood, so that we proceed in this chapter. Then we are going to discuss very important Nernst equation and many of its applications, not just one or two, many. Then the second part of this topic, second part of this chapter, which is electrolysis. What is lyse? Lyse means cut. So with the help of electrolysis, with the help of electricity, we are going to lyse something. We are going to lyse bonds. We'll see that in detail. Then we have another part of this. Our discussion for today is conduction. With the help of ions, how do we do conductions? And then finally, we'll see the different kind of cells in use around us, and a problem which is occurring, the problem that occurs to iron is commonly known as corrosion, and how to prevent it. All those things we are going to discuss. Let's quickly proceed to our very first agenda for today. What is electrochemistry? See, electrochemistry is a word which is made up of, it's a self-explanatory word, but it is made up of two words. One is electro and chemistry. In this chapter, in this branch of science, we deal with the interconversion of chemical energy to electrical energy and electrical to chemical energy. As I said, interconversion it is. So from here to there or from there to here, we are going to just move in back and forth. So electrochemistry is a branch of chemistry which deals with the study of how we actually change electrical energy into chemical and chemical energy into electrical energy. Since we need to bring a change, and to do so, we need a device, right? And that device is actually known as a cell. That cell would be of two types. One is electrolytic cell or electrolytic cell, as you wish to pronounce. The other one is either it is known as galvanic cell. Galvanic was the name of a scientist, or voltaic cell, or you can simply call it as electrochemical cell. There is a major difference between these two type of cells. We'll discuss what are those. First, and the very important difference is the electrolytic cell converts electrical into chemical energy. We use a battery, we use an external source of battery, external source of current, so that current is responsible to bring in some change, chemical change for us. Those chemical changes otherwise not very easy to do, or generally we say they are non-spontaneous in nature. For non-spontaneous, thermodynamics suggests that the free energy change should be always greater than zero. Those reactions for which delta G is greater than zero, those are non-spontaneous processes, right? If I give you a very simple example, not of a reaction, but just for a process. For example, falling of water from a waterfall from top to bottom is a spontaneous process. You need not use a battery, you need not use a pump. So it is a falling of water from the top, from the hill to the bottom is a spontaneous process, but getting back from the bottom to the top, you definitely need a motor, you need a pump. Otherwise, water won't go automatically from the ground to the hill, right? So that is a non-spontaneous process. Similarly, in chemistry, whenever the reactions are happening on their own, those are known as spontaneous reactions, though they happen on their own. So you need not use external agencies or external forces to have them occur, right? Now the second process, second kind of cells are galvanic or voltaic cell or electrochemical cell. Very, very, very important. This is majorly we use electrochemical cells in our daily life. They actually convert chemical energy into electrical energy. Chemical energy into electrical energy. And that process which actually is occurring, the chemical process that is actually occurring is spontaneous. It happens on its own and it results into current for us. It results into electrical energy for us. So chemical energy at a cost of chemical energy, we produce electrical energy. So this transformation or interconversion of energies into these electrical and chemical energy, this whole process, this whole study is known as electrochemistry. And the device that is required to do this change, to do this interconversion, is known as a cell. Make sense, everybody? Are you ready for this chapter to understand? Give me yes on the chat box. Give me yes on the comment box. Let's begin with the first kind of the cell. I have brought to you a picture on which it's very easy for us to figure out whether electrochemical cell or electrochemical cell and electrolytic cell, how do they differ from each other. Let me go to this side and discuss this right hand side graph first. Let's discuss that. All right, let me change the color so that I can highlight things. Okay. There are two things present. There are two compartments, one on the left side and one on the right hand side. The left hand side compartment is known as anodic compartment. Let me write it as this is anodic compartment. This is anodic compartment, and the right hand side compartment is cathodic compartment. Make sense? Okay. Now what happens on anode? What happens on cathode? What are these two things? First of all, anode and cathode, these are two type of electrode. Electrodes are made up of various species. They can be either gas, they can be major component could be a gas or a metal or various one. We have a list of those we need to look at. So this compartment has one electrode known as anode. This is anode. This electrode is cathode. Right now we are not discussing what is the material inside those cathode and anode. Just you need to know that there are two kind of conducting material present here. One makes anode, the other makes cathode. Understood? Okay. Now we have a voltmeter connected over here, or ammeter you can say, to measure whether there is a current supply or not. The voltmeter will measure how much voltage is created by this chemical reaction. This chemical reaction is spontaneous, has a delta G value negative, less than 0. So this reaction can occur. You need not to push this reaction hard so that reaction occur. No, it occurs on its own. This is a galvanic cell, right? Now next step is there is one inverted U-shaped tube dipped into these two compartments which are connecting the two. The one on the left and on the right, it is connecting those two. What is the function of that salt bridge? That we need to understand. Why do we need that at first place? That also we need to know. There is a flow of current happening. So I'm writing it down here for you that anode, you will always observe oxidation process, and on cathode you will always observe reduction process. All right. What is oxidation and what is reduction? Write down in the chat box, in the comment box, and tell me how do you identify a reaction is oxidation or reduction process based on electron gain or loss, right? Based on electron gain or loss, not in the terms of hydrogen loss or hydrogen gain or electronegative element given and taken. No, not all those, just the electron given or taken, electron loss or gain. Now I have an aqueous solution of X in the anodic compartment and aqueous solution of something Y in the canodic compartment. So the anodic compartment, since it has anode present in it, there will be oxidation happening. Now what is oxidation process? Suppose I have X solution, X aqueous would like to undergo oxidation. I have now told you this is going to be X solid, converting it to X plus aqueous and then loss of electron. I have just written out a standard equation. There might be 2 electron loss. Remember, there might be n electron loss, but just for the simplicity, just for the understanding purpose, I am writing this is called an oxidation process when one material increases its oxidation state. Here the oxidation state was 0, here it is +1, and the loss of electron is associated with this reaction. So this is an anodic reaction. So on anode there will be always oxidation, and this lost electron will start traveling via this wire, because wires are conducting in nature, and will reach to the cathodic compartment, which has a species ready to accept that electron. What is that? There will be Y present in the form of positive charge and aqueous. This electron is transferred via wire, will reaches to Y plus, and that Y will accept that electron, will undergo reduction to form solid Y. This is what happens in this electrochemical cell. With the help of this chemical reaction, I was able to produce some current here, which is witnessed by the deflection in this ammeter or voltmeter we use. Remember, this is the direction of flow of current of electron. The electrons are lost by the anode. Since they travel in this direction, anode has to be minus, cathode has to be positively charged. Understood? Anode 100% negative in this particular cell, which is galvanic cell or electrochemical cell in general. Anodic will be negative. There will be a loss of electron associated here, and that will be traveling towards the cathode. Since it is positively charged, it will attract electron. So positive and negative. This is a negative terminal anodic. This is positive terminal cathodic. Correct? All right. The direction of current is opposite to the direction of current electron flow. Since electrons are flowing in this direction, current will flow in the opposite direction. If I attach a bulb in between, the bulb will start glowing. The bulb will start glowing. Is every single thing correctly understood about a galvanic cell or electrochemical cell, except the part that there is a salt bridge? Why is it required? What are the components inside it? Every single thing is understood. Everybody give me a thumbs up in the chat box. Yes? All right. Now, my question to you, everybody, question is, what if I do not use this salt bridge? What if I try to understand that just by taking these two compartments, will there be any current? Will there be any current? The answer is no. The answer is no. You can ask me, sir, there is a flow of current. Flow of current is just enough for electricity production. Then why is there no bulb glowing? When the bulb is connected between these two electrodes, without use of the salt bridge, will the bulb glow? No. Why? Because only the external circuit is completed, internal circuit is still not completed. And then I ask you to complete the internal circuit. If I just mix the two containers, take only one tub, only one container, and dip anode and cathode, will there be any will the bulb glow this time? The answer is no again. Why? Because there is Wasteful external circuit. Why would electron take this long path to travel from anode to cathode? They will just travel straight. They will just travel in the solution itself. Why do they actually need to travel via wire? They will not do that. Again, the bulb will not glow. Now, to make this reaction facile as well as to make the cell working in condition, what do I need to do? I need to separate the two compartments as they are separated here. Also, I need to connect these two. Also, I need to internally connect these two reaction vessels, anodic and cathodic vessels, with the help of a salt bridge. This is of immense importance in this chapter, the use of salt bridge, and how do we select that? I will come to it in a moment. Let's come to this part now, which is representing an electrolytic cell. Okay. Now, do you notice that here cathode was positively charged, here cathode is not positive, it is negative here. This is one question that is asked in board examination again and again and again. What are the charges on the cathode and anode of electrochemical cell and electrolytic cell? The other side is anode. That was negatively charged in electrochemical cell, but here it is positively charged in electrolytic cell. The electrons are again lost at the anion and at the anode, because anode is the electrode on which oxidation happens. So this is universally true. This is universally true that the oxidation, irrespective of the nature of the cell, will always occur on anode. Reduction, irrespective of the cell, will always occur on cathode. So here, now you just need to put a battery and decide the charge. Since the oxidation is happening at the anode, the electrons will need to get attracted towards the positive plate of the terminal. Yes or no? Am I making sense? The positive terminal of the battery. So it will be attracted. So that anode will be always connected with the positive terminal of the battery. Understood? Very well. So what do we do here? We take a single compartment. Now we use an external battery, or what I can do, I can use this whole thing in the place of a battery here. Kaise? How? I will use this whole thing and just replace the battery with this electrochemical cell. Why electrochemical cell? What is the use of electrochemical cell? The use is to produce current. And what do I need from this battery? Current. So why to use a battery? Battery is basically electrochemical cell. So I will use that cell and keep it here so that the current is supplied by the electrochemical cell to function this electrolytic cell. Are you getting my point? Are you getting my point? What I'm saying, I have an electrolytic cell, I have electrochemical cell, I will use electrochemical cell here, which is nothing but a cell, which is battery. Collection of cells are battery. It will give the electron, it will give the current required to do this non-spontaneous reaction having delta G greater than 0. This has delta G greater than 0. Understood, everybody? Awesome. Brilliant guys. So this was a very brief introduction of electrolytic and electrochemical cell. Is everything clear so far? Everybody? Awesome. Let's move to the next part, which is very much ignored in electrochemistry, but I want you to be very focused. This is my personal favorite chapter. In the case of electrochemistry, when we do some reactions, suppose I create a system. Once I separate the two with the help of some glass frit or some semi-permeable membrane, or any kind of separation is created between the two solutions. On the left hand side, I have NaOH of some concentration, some random concentration, okay, some random 0.01 molar NaOH I have taken on one side. Now on the other side, I am taking 0.001 molar NaOH. Now I can see that both the sides, the concentrations are not same. There will be flow of water from here and there. Correct, everybody? Now, we know that Na plus and OH minus is a strong electrolyte. It will split into Na plus and OH minus. Both will try to rotate, both will try to move around and try to pass through this Na plus and pass through this membrane. You don't think that only the solvent molecule will pass. Na plus and OH minus are also allowed to pass through this. Okay. Now, if you check out the flow of or the speed of ionic mobility of these two are very different from each other, very different from each other, what will happen that this OH minus will travel faster, much faster than Na plus, and then Na plus will start creating and OH minus will start creating some charge imbalance. This side the charge positive will start accumulating, this side the charge negative will start accumulating. This is the reason that why don't we use just one single dabba, and then separate directly with the, there is an anode here, there is a cathode here. Why don't I dip that solution here? Let's say these are the two containers separated with the help of one membrane. Why don't I just use a membrane? Why do I need to use a salt bridge? Uska jawab de raha hu main. Why am I using that? This particular problem occurs when I am separating the anodic and cathodic component with the help of just a membrane. This is the third case. First case, I can take only two boxes, two compartments, and then dip electrodes in it, bulb will not glow. Second one, I take single compartment, mix anode and cathodic compartment together, and then use anode and cathode, again bulb will not glow. Then the third one, take the single container but separate A and C anodic and cathodic compartment with the help of a membrane. Again light, again the bulb will not glow. Yes, perhaps for a second there will be a flash. Perhaps for some second, 1 or 2 seconds, there will be a flash, but then the light will not be there anymore in the bulb. And why is that? Because if electrodes are not connected internally, very important point, if they are not connected internally, the cell generates electrical energy. After some time, electrodes get polarized. Dekho, see here, there is a positive and negative charge. There will be charge imbalance, due to which this is known as liquid potential. Liquid junction potential. Liquid junction potential. Very much ignored concept in electrochemistry, but it is very important. We should know that if a question comes to you in your examination that why salt bridge is required, mention this point. To get rid of junction potential, to get rid of liquid junction potential, we need salt bridge. My guarantee to you, nobody will ignore your answer. They will just check this with a 100% enthusiasm. Who is that student who knows there is a liquid junction potential also coming into this picture? And that cell will be 100% working if you ignore, if you somehow take care of liquid junction potential. And how do we do that? This is the junction between the two liquids, everybody. Junction between the two liquids, anodic and cathodic liquid. Therefore, there will be some sort of polarization happens, and then the current will stop flowing. This stops working of the or the electron flow will stop. Is this liquid junction potential clear, everybody? That why do we need to have two different compartments and both of them to be joined with something different. Something different is now known as salt bridge. Clear? Why cannot we use both of them together? Why can't we use just single one compartment? Why can't we why can't we have one membrane separating the two? Nothing will work. We need to use salt bridge. Very important. Salt bridge function is very important. Let's move to the point, everybody. Now I have brought to you Daniell cell. Now what is Daniell cell? Daniell cell is an example of one particular example of galvanic cell. On the anodic side compartment, anodic will be always on the left and cathodic will be always on the right. I have zinc sulfate solution. Zinc sulfate solution meaning ZnSO4 aqueous. My question to you, everybody, zinc sulfate solution color. What's the color of zinc sulfate? Inorganic chemistry is my first love, let me tell you, and I will be keep on asking you inorganic chemistry question during physical as well as organic chemistry revision. Zinc sulfate solution ka colorless. Arey sir, we can see that colorless it is. So why is it colorless? ये भी समझा देता हूँ. Zinc, what's the oxidation state? Zn2+. What is the electronic configuration, it is 3d10 4s0. If you have no unpaired electrons present in the d orbital of the transition elements or the d block elements, there will be no possibility of electron jumping from lower HOMO to LUMO, and absolutely no color then. So zinc 2 plus will be colorless material. Zinc sulfate, zinc 2 plus is colorless material here. Now since it is an aqueous solution, and aqueous solutions, zinc sulfate solution aqueous is a 100% electrolyte, it will dissociate to produce zinc 2 plus aqueous and sulfate SO4 2 minus aqueous. Okay, these are the two species present in anodic compartment. Let me write it as anodic compartment A. On the right hand side, that is cathodic compartment, there is blue color copper sulfate solution. Blue color copper sulfate solution. Can anybody tell me what's the use of copper sulfate? What's the use of copper sulfate? Anybody? What's the use of copper sulfate? Let me tell you. Copper sulfate prevents algae growth. Anywhere you when you see that there is algae production happening, just take some amount of copper sulfate and just dump it there. It will be a blue color ka water everywhere, and then it will stop. It will prevent the algae growth. Understood? Okay. This is my anodic compartment. This is cathodic compartment. We know these are the cations and anions present in the medium. But what is the operation? What is the process happening at anode? There will be oxidation process. And whose oxidation? The material of which anode is made. What is the material here? Zinc. Zinc solid. See, you have to mention their phases, their concentration, everything in electrochemistry chapter. This will start producing zinc 2 plus. Since zinc will start getting used up, it will produce more and more and more of zinc 2 plus. Those two lost electrons will start traveling towards the cathodic compartment. Let me complete it by writing 2 electrons. There are 2 electrons present plus 2 electrons. This is called oxidation half reaction, OHR. Oxidation half reaction. Those lost 2 electrons will start traveling via this wire. Let's go very slow and gradually in this chapter to master it, guys. This is very, very important, not just for your boards, but for NEET, but for JEE, for any sort of competition examination you might be preparing for. Now, on the right hand side, what is the ion present? Everybody, copper 2 plus. That copper 2 plus will take up these 2 electrons to form copper solid. This is known as reduction half reaction. Reduction half reaction. Here the reduction is happening and here oxidation is happening. Check these 2 reactions. Here also I have mentioned that there is reduction and oxidation happening. Now, how do we actually represent this whole electrochemical cell? That is known as cell representation. That also we are going to learn in a moment. Always anodic compartment is written first, then cathodic compartment is written. So AC, air conditioner wala, anodic first, then cathodic compartment. This is how we represent a cell. Alright, we will discuss that in a moment later. Now, I think we have discussed everything about this electrochemical cell except this salt bridge. Now, I am here to explain you why this salt bridge is so very important. Why do we actually need? I just told you that the anode, which is zinc solid, starts undergoing an oxidation process. So, can I say that here the amount of zinc 2 plus will start getting more? It will be start getting increasing. And here copper 2 plus is accepting 2 electrons, so the amount of copper 2 plus will start reducing. Right? Let me change the color of the pen if it is not properly visible. Okay. Okay. So I said here copper 2 plus, amount of zinc 2 plus. Lovely, lovely. Now this is easily visible. Zinc 2 plus ka concentration will start increasing, not decreasing, increasing. And then copper 2 plus Copper 2 plus will start undergoing reduction and its amount will start decreasing. Suppose in the beginning I had 100 molecules of copper sulfate. So now the amount of copper 2 plus will be greater than sulfate. Yes or no? Why? Because earlier when they were 100 and 100, now because of more copper sulfate, more because of copper sulfate reduction, what's going to happen? Copper 2 plus concentration will start dropping and sulfate concentration will start remaining the same. But upon comparison, we see that copper 2 plus concentration is reduced. Here, overall concentration, zinc 2 plus will be more than sulfate concentration. Do you see that there is a charge imbalance created again here? Charge imbalance means here the positive charge seems to be more than the negative charge. Here the negative charge seems to be more than the positive charge. There is another issue. There is a problem now. What will happen eventually? They will start fighting for the charge balancing, and that cannot be done since electrons traveling over there. Zinc 2 plus is still looking for its counterpart, that is sulfate. So what we need to do it is to satisfy it, is to relax it by providing it some other or the same cation, something that does not participate in the reaction, something that does not hinder the reaction, something that does not interfere with the reaction. Any sort of reaction, not just the redox reaction, but with the precipitation, decomposition, neutralization, any sort of reaction, it should not do. So we will be filling this salt bridge with one sort of electrolyte, and that electrolyte will have A and B component, A plus B minus. In general, now A can have more charge, B can have more charge, they can be monoatomic, they can be polyatomic also. For example, NaCl, very simple NaCl. Now what's the function of this? I will be using the salt bridge with the cotton plug on the bottom, so that the ions don't fall. Also these anions will be digested, or they will be stored in agar-agar jelly. Agar-agar jelly is also used to prepare some sort of cakes, some sort of food additives, items. Now this A plus and B minus, here what was less? Zinc 2 plus is more, anion is less. So what this salt bridge judicially will start dropping something which is less in the solution. Who is less? Anion is less. So it will start dropping Cl minus inside, so that charge imbalance is treated, is prevented, is no more there. But remember, for zinc, oh, this is 2 plus. Zinc 2 plus requires how many anions? Two of these. Cl minus. Cl minus carries only one minus charge, so I need two of those anions, so that zinc 2 plus ka charge can be satisfied or neutralized. And here in this side, I have copper 2 plus less in amount, so I will be adding from here K plus. So K plus will start getting increased over here. And how many do I need here for sulfate? Two of these potassium every single time. Now there are few properties of these salt bridge. Do you understand the function of this salt bridge or the use of this salt bridge? The first one, it completes the internal circuit. What did I say, guys? What did I say? It completes the internal circuit, not the external circuit, internal circuit. It prevents the mixing of the two solution. I need to use, it also prevents liquid junction potential. These three important points, these three important reasons. Now what are the qualities, or what are the requirements of something salt bridge to choose? How do we, should we choose a random salt bridge, or some important facts we need to take care? Yes, the fact number one, salt bridge should be or must be chemically inert. Chemically inert. Should be chemically inert. What does it mean, chemically inert? It should not participate in any sort of nonsense reaction. I don't want it to participate in my reaction. I don't want it to do some kind of redox, decomposition, neutralization, precipitation reaction. It should also be electrically neutral. Electrically neutral. Now what does it mean? Electrically neutral means it should not have charge imbalance on its own. तब क्या फायदा यार, है ना? Now also it should have same ionic mobility, same ionic mobility, same ionic mobility. किसकी? Whose mobility? A plus and B minus. They should have same ionic mobility. It should not have happened that I need, let me go back, should not have happened that, oh, Cl minus is coming faster than potassium plus. Cl minus is coming faster than potassium plus. तो क्या फायदा? Again there will be momentarily there will be charge satisfaction, but again the bulb will stop glowing. So I need, if there is a cation or anion imbalance, immediately the salt bridge should dump a cation and anion wherever it is required, but the same speed. So their speed of release, their speed of mobility should be the same, right? Understood? It should be ionically, it should be electrically, chemically inert. It should not participate in any sort of nonsense reaction. Now this picture I love the most. Why? Because it represents every single thing that undergoes in a Daniell cell. So one side we have anode, another side we have cathode. I have taken in a zoom in portion of this reduction reaction, zoom in portion of this oxidation reaction. The two electrons are lost and that zinc which was present on the anodic surface is no more present. See this, zinc is gone in the form of zinc 2 plus, and 2 electrons are lost, and those 2 electrons will start traveling via this wire and reaches to the copper 2 plus. Copper 2 plus will accept those 2 electrons and start depositing on a cathode. Beautiful reaction, beautiful reaction goes over here. Now salt bridge is used, NaCl for example, wherever there is a need of cation and anion, it will start adding. So what is the use of the salt bridge? What's the use of the salt bridge? Completes the internal circuit, and it should be having chemically inert, electrically inert, same ionic mobility of the cation and anion, and they are actually packed in agar-agar jelly. Okay, so overall reaction of this cathode and anode reduction here can be written like zinc 2 plus, or zinc actually is undergoing oxidation plus 2 copper plus, aqueous. Mention all these phases, everybody. It's good for scoring better marks. 2 plus and copper becomes solid. Is there any electron in this reaction? Are you seeing any electron written in this reaction? No. Which means that a full cell reaction will have no electron in it. I'm not saying electron gain or loss will not be there. Electron gain and loss will be the same in oxidation and reduction half reaction. When you add these two, electron should not be there. If you see any electron present in that reaction, it's not a full cell reaction. Here there is no electron here, so that represents full cell reaction. Rx means reaction. Understood, everybody? Bolo bhai, bolo. Okay, good. Now, what is electrode potential? What is this thing, electrode potential? Hai kya? What is that? Now you see that there is a this is just for the graphic, just for the representation. Here, let me go back and explain it to you. On this plate, the electrons were lost. This plate will start getting a positive charge. Yes or no? Hai ki nahi? This plate will start getting a positive charge. The ions which are present in the medium are positive as well as the negative charge. Clear? Now the positively charged plate will attract a positive or a negative charge anion. See, I have already answered. It will start attracting an ion towards it. So there will be a positively charged plate. Then there will be an ion, and those anions will be surrounded by cations. बात समझ में आ रही है? There will be cations. There will be a positively charged rod because it has lost electrons. Also, then there will be negatively charged anions from the solution. Then there will be positively charged cation again from the solution. This actually creates a difference in the concentration of these electrolyte of cation and anion just around the electrode, and after that medium, after in that range, in that whole solution, there will be a concentration gradient, very small amount, but there will be very small amount of concentration gradient, and due to this concentration gradient, there will be charge separation start developing. I am not saying charge imbalance, charge separation will start developing. Due to that, if the two charges are separated, what happens? If the two charges are separated, what happens? Potential difference started coming into the play. That potential difference on one particular electrode here, if it is anode, is known as anodic potential. The same process is happening over here also, because cathode is now negatively charged. It will be having some concentration of 2 plus ions and now 2 plus cations around it, and then there will be concentration gradient, due to which the cathode will also experience some potential. Now you have anodic potential, cathodic potential. They too, depending upon their own composition, their material, will have either same or different electrode potential. And then electrode potential between these two, cathode and anode, is known as overall E cell. Cell which is made up of cathode and anode is known as E cell. Do you understand? Now please notice the zinc rod which was undergoing an oxidation. See, it start eating up. It is almost finished. And the copper 2 plus which has started getting deposited on the cathode, now it has started become thicker and thicker and thicker. What does it mean? I need to periodically replace anode in electrochemical cell, because anodes are keep on consuming, and this particular process is very important. I can use it in industry for many various purposes. Understood everybody? Bol do bhai? Pakka? Next. Yeah. Now I said the potential difference developed between an electrode and an electrolyte of the solution. मैंने बोला electrode and around that there will be electrolyte. Due to the concentration separation, concentration gradient, charge will be very finely separated, and due to that there will be electrode potential, and this electrode potential will force the electron to start traveling from one electrode to the another, and then there will be EMF. EMF means electromotive force. That electromotive force, the driving force that pushes the electron away from anode and pulls them towards the cathode, that is known as. So there will be electrode potential of cathode that tries to pull the electrons, and there will be positively charged, there will be anode also which will try to push the electrons away from it. Hence this overall E cell comes into the picture. Okay everybody, this is what you are seeing here is the E cell, the difference of these two electrode potentials, anodic and cathodic electrode potentials. Okay, the electrode potential which is determined by the concentration of all the solute is unity. What is this now? When we keep the solution concentration to be 1 molar, 1 unit, and we fix the temperature and pressure to be the standard value, STP, standard values, then we measure what is the potential. That is given a separate name, standard electrode potential. Standard electrode potential. Now it becomes a real challenge. How do we actually find electrode potential of a single anode or a single cathode? Did you think about it any time? How do we actually find the anodic or cathodic potential, electrode potential? We need to actually use a cathode for my anode of interest, and I need to find anode for my cathode of interest, so that I set up a cell. I already know the value of cathodic potential, and the cell will provide me a value from which I can calculate anodic potential. Or I can use an anode of a known potential and then use a cathode of unknown potential, make a cell of the two, use this to find out what is the overall cell. Again the question, how do I use one particular anode or cathode of a known potential value? That's impossible to find out. That's impossible to find out. So what we have done is we have used a standard reference cell, standard reference electrode. We use a standard electrode reference. In general, 90% of the time we use She. She means standard hydrogen electrode. And I will repeat, I will keep on repeating. If you don't listen to me, standard hydrogen electrode by convention. By convention its electrode potential value is set to be equals to 0 volt. It's ये है नहीं, it is not 0 volt, but by convention it is set to be 0, so that whatever value that you see here is equals to the difference of the anodic and cathodic potential. If I am able to fix one of the value 0, so what is this value going to represent? It's the other one already. It's the other one already. My calculations are so much simplified. Right, everybody? So she ka electrode potential is considered by convention to be 0. So there are two kind of electrode potential. One is known as oxidation potential. The other one is known as reduction potential. How do we actually represent oxidation potential? With the help of E, OP, overpowered wala. Wow. EP. So E of that oxidation potential will be represented. So suppose I am representing for zinc. Zinc, first of all, write its reduced species, then slash write down its oxidized species. If anybody reads this, will try to understand that you mean to write oxidation potential. On the right hand side, if you have reduction potential, to mention E of Zn 2 plus 2Zn. What is this process, everybody? Reduction process. So zinc 2 plus undergoes reduction to form zinc solid. This will represent reduction potential. If nothing is mentioned in the question, they do not say that what kind of potential you mean. So it has to be always considered to be reduction potential. ये किसका आदेश है? Whose order it is? Whose convention it is? By IUPAC, International Union of Pure Applied Chemistry. Okay, now this is my she used as a cathode here in this particular question, in this particular setup. She is used, and on the left hand side I'm using anode made up of zinc. So I do not know anything about zinc here, nothing, not at all. Anything means that no electric potential is known, but for she I know that it's 0. So whatever cell value that you are seeing over here, 0.76, will represent zinc oxidation potential. All right, everybody, the potential of this cell, potential of this anodic cell. Clear? Good. बोलते रहो भाई, बोलते रहो. Now, the potential difference between the two electrodes is known as cell potential, and that is going to represent E cell, which is equals to ERP, reduction potential of cathode, minus ERP, reduction potential of anode. If you trust me, always follow just this. Don't be confused with oxidation potential and reduction potential combination, or oxidation potential combination. Just use this straight away. Just single formula. There are thousands of formulas to be remembered in chemistry. Why to give your head a lot of pain? Just take this simple formula: ERP of cathode minus ERP of anode, C minus A. Okay. Now the cell potential of a galvanic cell at the standard state will be represented by E naught. So I am writing it as E naught, E naught, E naught. What does this naught represent? The concentration of the anodic compartment taken is 1 molar. Concentration of cathodic compartment is taken is 1 molar. Temperature at which these two compartments are operating is according to STP. Pressure is also according to STP. If at all there is a pressure of gas, any gas, but particular gas is used. For example, in she, we use standard hydrogen electrode. We use HCl solution as and a hydrogen gas. So then hydrogen gas temperature, pressure, everything has to be maintained properly. So most commonly reference electrode, reference से नाम समझ में आ रहा है? With the help of the name, is it understood? Reference with respect to she, we are going to arrange the electrode potential of various elements, and that is what you have a table in your NCERT also, that is known as electrochemical series. Those values are with respect to she. Understood? With respect to she, just like electronegativity of an element is with respect to hydrogen. Similarly, this particular electrode potential is also according to she. Understood? Good job. Now, this E cell is represented as, I just told you, E naught cell is equals to E of the cathode, but it has to be reduction potential. Standard reduction potential, SRP, of the substance reduced. Where do you observe reduction? On cathode. E naught of anode. E naught of anode, but it has to be reduction potential. SRP of the substance oxidized. Remember, the processes are not both reduction. Here there is oxidation, here there is reduction, but the potential, both of them are taken in the form of reduction potential. One more thing you should know, that E cell of reduction potential will be equals to for any process, for any element, for any single cell, if you represent E naught of let's say zinc, for zinc 2 to 2 plus, E naught zinc 2 plus to 2 plus, if it is equals to x volt, for zinc 2 plus will be equals to how much? Minus x volt. So we can generalize that E oxidation potential of anything is equals to E reduction potential, or vice versa, or vice versa. Remember that, very very important. This is the thing I was telling you, that we need to learn how to represent a cell. The cell notation, extremely important. Every year they ask you this question on arrange this reaction. They will either give you a cell and ask you to represent a notation, or they will give you a cell notation, ask you to write the reactions. Clear ho gaya? Now on the left hand side, always AC. Oxidation process always on the left, reduction process always on the right. So what do you see over here? First of all, you need to mention what is the anode. Always mention its phase. So zinc solid, separate it with either a slash or a comma or a semicolon. I'm repeating. Separate the two phases. The two phases. Zinc solid is separated with zinc 2 plus aqueous. These two phases are separated with the help of either a slash or comma or semicolon. All the things mean the same. Then you need to mention what is its concentration. Let's say I write C molar. Let's say I write C molar. It is essential to mention. It is essential to mention the concentration, their phases, their charges. Otherwise, this cell will be treated incomplete. Now, you need to put a double line which represents salt bridge. Salt bridge. Now, you need to mention the copper 2 plus ka species aqueous. Write down its concentration. Let's say it is C2. It was, let's say, C1. C2 molar, and then separate it with single vertical line with another phase of copper, that's copper solid. Clear everybody? First of all, write solid, then aqueous, then another aqueous, then this side always anodic compartment, that side cathodic compartment. Both of them are separated by a double line. Clear? Good job. Okay, now the delta G is actually related with the thermodynamic property. That delta G, the thermodynamic property, it is related with E cell also. How is it related to E cell? We know that delta G is directly proportional, or is equals to the useful amount of work. Here what are we doing? Electrical work. And that electrical work is equals to charge times the electrode potential. Charge times charge multiply E cell. And the charge, how much charge is actually flown through the circuit, is equals to the number of electrons transferred into Faraday. So that actually becomes delta G equals to minus NFE. Sir, why minus? Because this is a spontaneous process. To have a minus value, to have a delta G negative value, we need to have a minus over here. Delta G is equals to minus NFE cell. For a standard state, it will be delta G naught equals to minus NFE naught cell. Understood everybody? So far so good? Bol do bhai. Bolte raho. Okay, good. Now we need to know that why do we need to really understand, why do we need to really learn about Nernst reaction? See, I told you, in electrochemical series, we have a list of the chemicals, list of the anodic and cathodic potential, but all of them are at standard states. 1 molar. Don't you think this limits the utility of the table. So why? How? Suppose I want to use a 2 molar solution now. Suppose I want to use at 300 Kelvin temperature today. I want to use the same cell but at different temperature, different concentration, what are listed in the electrochemical series. I do not know their potentials now. What to do? Should I wait for some other miracle or some other reference electrode to be made for every single temperature, for every single concentration, and then make a database? No, that can't be done. That's insane. So what we do, we have created Nernst equation which takes care of the temperature and it takes care of the concentrations of the solute, which includes the composition, which includes the pressure if the gaseous components are also used. We know this formula, the delta G is equals to delta G naught plus RT ln Q. What is Q here, guys? Q is reaction quotient. I am very sure you know reaction quotient from chemical equilibrium perspective. Suppose there is a reaction A of A reacting with B of B in equilibrium with C of C plus D of D. Now can you write Q, reaction quotient, for this? The concentration of C power C into concentration of D power D divided by concentration of A power A, concentration of B power B. This is a reaction quotient. If you write this reaction quotient at equilibrium, this will be equals to K, equilibrium constant. Equilibrium constant. If the reaction is having, this equation is 100% valid for any sort of reaction, any thermodynamic process. Since we know delta G is equals to minus NFE, I can put that equals to minus NFE. That should be equals to minus NFE naught. And that remains as it is, plus RT ln Q. Clear? Now E of the cell should be equals to E naught of the cell minus RT by, I am dividing the entire equation by NF. This becomes my final equation known as Nernst equation, which helps us in taking care of the temperature. Check please that there is a temperature here, R is constant, number of electrons transferred is constant, Faraday is a number 96500 constant. Q is this which takes care of the concentration of A, B, C, D, the reactants and the products, right? This is known as Nernst equation. There is another simplified way. We can say it's equals to E naught minus 2.303 RT by NF into log. I am converting ln to log. This is another way. Further, if you put down the temperature 298 and R value also, what will happen to this equation? It becomes E naught minus 0.06 log of Q divided by NF divided by N. Understood, everybody? This is an equation you can use by putting down the value of F, by putting down the value of R, by putting down the value of temperature at 25 degrees. This is at 25 degrees. Remember, be careful. If anybody asks you, is this equation Nernst equation? Is this equation Nernst equation? The answer is no. This is modified Nernst equation. क्या फर्क पड़ता है? What's the difference? Yes, it is different because you have made this change. This is not Nernst equation. Nernst equation is this. Clear, everybody? बोलते रहो भाई. Clear? चलिए आगे बढ़ते हैं. Now this is what I just drew for you. If the reaction has achieved an equilibrium, suppose A is in equilibrium with B, at that situation delta G becomes 0. Also delta E equals to 0. If delta G is 0, delta E is 0, not delta E, E is 0. E is 0. Now what will happen? E means E cell. Then delta G naught is equals to minus delta G naught equals to minus RT ln K. That K is K equilibrium. This is the equation you must remember. Delta G is 0, delta G naught is never 0. Now I can say that minus NF E naught cell is equals to minus RT ln of K minus minus cancel E naught will be equals to minus cancel हो गया RT, this will be equals to RT divided by NF into ln of K. Check please. If you want to put down the value, of R and T and R and F, then you can say this as this is at one particular temperature. So ln of K from here is equals to NF E naught divided by RT. Check please. This is the equation that I have on the left hand side also clearly written. Now when you change this ln of K to log of K, this 2.303 factor comes and get into the denominator. So this is the application of Nernst equation. You can calculate E naught of the cell at various concentrations. Can be calculated, at various temperatures can be calculated. Also from here we can calculate equilibrium constant. From equilibrium constant we can calculate alpha. Alpha is degree of dissociation. For any sort of material, degree of dissociation can also be calculated. Very, very, very important concept of electrochemistry, Nernst equation. Clear everybody? बोल दो भाई. Okay, चलिए आगे बढ़ते हैं. This is your electrochemical series which is developed with respect to, in reference to hydrogen She, standard hydrogen electrode. The top elements that you are seeing over here are the strongest oxidizing agent. Let me explain it to you. What are oxidizing agent? The oxidizing agents are those which will oxidize others and in return they will reduce themselves. They will oxidize others and they will reduce themselves. So suppose I have F2. F2 is one of the strongest reducing agent, strongest oxidizing agent. Strongest. Why? Because it is the most powerful. It is the most powerful electronegative element that exists in the periodic table. So F2, if you offer it some electron, do you want it? Fluorine says, yeah, yes. જોઈએ છે. Have you seen that movie? What is the name of that movie? अरे चुप के જોઈએ છે. 2F minus. So this takes up the electron nicely. It becomes an extremely powerful species to undergo reduction. Therefore, itself is undergoing reduction. So powerful oxidizing agent. OA oxidizing agent. So when you move from top to bottom, you are seeing there are metals, and metals are born to lose electrons. And now we can see that the potential value here. What is the potential value, guys? This is standard reduction potential. Every potential value that is denoted here, that is written down here in the standard electron potential electrochemical series, is representing SRP. They are in the SRP format. Higher the positive, higher is the SRP, standard reduction potential. Better or easy, better is reduction, or easier or better is the reduction, and stronger will be stronger OA. Did you follow? Bolo, did you follow? So 2.87, and when you're moving negative, oh, there is a 0 also. For whom? For whom it is? For hydrogen, H plus. H plus taking up electron, becoming H2 gas, and that value is 0. Is it really 0? No, by preference, for reference, we are making, by convention, it is considered to be 0. All right. Now these values are at 298 Kelvin, that's standard value. Higher is the oxidation value, higher is the SRP, better or easier will be the reduction, and stronger will be that oxidizing agent. Can you compare the stronger and the weaker reducing agent, oxidizing agent here from this table now? One question expected from this particular table. Let's move to the next part. Now, very important application of this particular delta G and E cell is that when you are provided with these 2-3 reactions and you are asked to build a relation between these two, then what to do? Shall we say that this is my reaction number 1, this is my reaction number 2, this is my reaction number 3? If reaction number 1 is written like that, Fe2 plus is taking up 2 electrons and becoming Fe, that's equation number 1. And then I'm writing it reverse, okay? I'm writing the second reaction reverse. So Fe gives 3 electrons plus becoming Fe3 plus. This is my second reaction. The third one is Fe3 plus forming, okay, Fe3 plus is taking up the electron, and how many? Just 1 and becoming Fe2 plus. This is my third equation. Can you make the third equation from the first two equation? Let me rewrite this. This is my Fe3 plus taking up 3 electrons becoming Fe, and that has equation number 2. From these two, I want you to develop equation number 3. What mathematical operation will you apply on equation number 2 and 1 to get 3? So let's first of all check. Do you need Fe3 plus in your reaction, final reaction? Yes. So equation number 2 will be written as it is. Do you need Fe2 plus? Yes, but on the product side. So minus 1, that should be equals to 3. Let me explain once again. You want to keep Fe3 plus as the reactant, so you have to have a positive sign with reaction number 2. Now you want to have this Fe2 plus, which is a reactant here, but as a product in the final reaction. So you need to make this product. And how do I make this product? By multiplying this reaction with minus 1. So the same operation would be done with E also. So E3 will be equals to E2 minus E1. Very important concept, very important. One question for sure, 100%. E3 will be equals to E2 minus E1. But can we do that? My question to you, can we do that? Is it right? Can you add electrode potentials? Are electrode potential additive in nature? Is it extensive or intensive in nature? You need to think all these. Now, before we do that, we know that delta E or E is related to delta G minus NF E is equals to delta G, and well, we very well know that delta G is additive in nature. Why not use delta G then? Let's replace for the first reaction how many electrons? N is equals to 2. For the second reaction, N is equals to how many? 3. What is N here? The number of electrons transferred, lost or gained. In the third one, N is equals to how many? Just 1. So for the second reaction, it is minus NF, how many? E2 minus of minus. Since I have flipped the reaction E1, so this E1 will also be getting flipped because E will get negative charge, minus NF E1. Are you following what I'm saying? E1 value will no longer be E1 since I flipped the reaction. E oxidation potential is equals to minus E reduction potential. Okay, that's equals to NFE minus NFE3. How many electrons in the second case? 3. Minus, minus, minus. Let's cancel minus. So here E2 into N should be equals to, should be plus. Should be minus. I'm just taking 1 minus cancelling. I'm cancelling 1 minus 1 E1 equals to N E3. How many N in E2 second? 3. 3 times E2 minus how many in the first case? 2. 2 E1. How many in the last case? Just 1. Do you see that? Do you see that? Do you see that? What we were originally doing, that is wrong. Because electropotentials are not additive in nature, but delta G is. So whenever you see there is a final equation, if it still has an electron, I'm repeating, if it is still having electron, is it a full cell? No. If it is not a full cell, you cannot just add or subtract electropotential simply. Directly, you cannot do that. Suppose I had no electrons involvement at all, no electrons here, then you can easily do, because then electrons will overall get cancelled in the final. Understood? In the final equation, the delta G equation, the number of electrons will be the same. They will anyways be cancelled. Unknowingly, you will be using the same. This and this, they will be the same. But here, when you have 1 or 2 electrons left in the reaction, which is not a full cell, will still be having some difference in the electron present over there. You need to use delta G relation to find relation between various delta EMF and delta G. I hope this is very clear to you. Let us proceed to the next part. There are various type of electrodes, although you need not know them all of these in detail, but just name metal soluble salt, which we have used in Daniell cell, for example, galvanic cell, gas ion electrode, she is the example, standard hydrogen electrode, redox electrodes, metal insoluble electrode, amalgam electrode. By the name you should know there are various kinds of electrode that exist. Now this is my electrolytic cell. I have already described what is going on here, what is the cathode, what is the anode here in the very first slide. This part is anode and it is positive here, this part is cathode and that's negative here, not positive. Remember carefully. Whenever you forget, just attach one anode and one cathode. You should know that the anode and cathode ka position is never ever going to change. Just connect it with a small battery and you are ready with the sign. That's positive, that's negative. Check please. Clear? Always do that. I always prefer to take help from a very small sized battery. Now, electrolytic cell helps us in doing non-spontaneous reactions, as I told you before. The non-spontaneous reaction, for example, NaCl, molten NaCl electrolysis. Although this process has a delta G greater than 0, but with the help of external voltage source, we can make this reaction occur. So what will happen overall? Oxidation of Cl minus on the oxidation. Where does oxidation happen? And on anode always. So Cl2 gas will be liberated. And sodium plus, which does not want to ever accept electron, hence it's a non-spontaneous reaction, but under the influence of voltage you can ask it to accept the electron. So you have got a sodium, you have got chlorine obtained. Now when you react sodium with water, now you will obtain NaOH and Cl2. Very important reaction, NaOH and Cl2, both useful materials can be made by just doing electrolysis of molten NaCl. Clear everyone? Shall we proceed? Awesome. Bolte raho bhai. This is a preferential discharge of ions. If you have various ions present in the medium, which ion will undergo oxidation or which will undergo reduction first, which according to their ease. Do you see that? They, from top to bottom, they're saying that silver would like to undergo oxidation very soon. So you have copper based material. Then mercury, here you are having copper 2+. Okay. Mercury will also undergo oxidation, also undergo reduction. Then you will be having silver. Then you will be having platinum. Then finally you'll have gold. Copper, mercury, silver, platinum and gold. You can use this mnemonic to remember छापा से याद रख सकते हैं. And if you want to check over here, hydrogen is present somewhere here. Any element which is above this, would like to remain in their ionic form, in their oxidized form relatively. And the elements which are present below hydrogen, they would like to be in their elemental form. So the elements which are present below, they prefer reduction. The elements which are present above hydrogen, they prefer oxidation process. As simple as that. And in the case of anions, SO4 2- does not undergo oxidation. Iska kya hi oxidation? It's already present in 6+ oxidation state. Water wants to, OH- wants to undergo oxidation readily. Then iodide, bromide, chloride and nitrate. You just need to have a look. This will be helpful for your questions. Okay. Now let's discuss Faraday's law of electrolysis. Very important. Faraday has not done a rocket science for us in this particular electrolysis, but a logical study was done. He says that the weight of material which will be deposited during the electrolysis process depends upon how much charge is supplied. It is directly proportional to how much charge is supplied. So W was found to be directly proportional to the charge. Q is the charge. All right. Now, W is the mass deposited or liberated on one particular cathode or anode. Obviously, it will be anode, or it can be anode also. When you remove this proportionality, you have a Z. Z is known as electrochemical equivalent, and that is equals to equivalent mass divided by F. And that F value is 96500. Everybody knows. This is the first law of Faraday. Second law of Faraday, he says that if I connect two cells together and supply the same amount of charge to both these cells, the amount of substance liberated on the cathodes will be same. The amount will be in the chemical equivalence. They're proportional to their chemical equivalence. Now, once it is understood, the mass deposited at the electrolyte will be in the ratio of their Z also. Z also, very simple, very straightforward. Let's see how we can understand that. So, for the first one, we can say W1 will be the charge directly proportional to Q1, and W2 will be equals to directly proportional to Q2. Since Q1 and Q2, they are same. So, can I say that W1, let's take a ratio, W1 divided by W2 will be equals to Q1, Q2, cancel, Z1 by Z2. Z1 by Z2. Is this clear? Is this clear? Is this clear? Is this clear? Check this, please, everybody. This is what I was saying. Let me go back. This is what I was saying will be the ratio of their electrochemical equivalence. Understood? Awesome. Now, here, this is the second case now. When Z is known to be equals to equivalent weight divided by 96500, so Z1 will be E1 divided by 96500, Z2 will be this ratio. Now let's take ratio of Z1 by Z2. 96500 constant value, they will cancel each other and it will be E1 by E2. So this also proves the second statement that it will be proportional to their chemical equivalences also. Weights, chemical equivalent weight E also. Understood, everybody? Is the second law clear? Is the second law of electrolysis clear? Good. Okay. Now we need to know what is conductance. There are two types of conductance, everybody. One is called electrical conductance, the other one is metallic conductance. In metals, the conductance is due to the presence of electrons, and they hop from one side to one place to the another. It's a hopping mechanism that they follow. But in the case of electrical conductance, you need to have some ions present, and those ions follow Groth's hopping mechanism. And eventually they conduct electricity. The ions move around. The ions they are mobile in nature, and due to that they transfer their energy from one to the another. Let's read out few rules, few properties of metallic and electrolytic conduction. This is very important table, guys. So the flow of electricity takes place without the decomposition of the material, but here the decomposition happens. So there are two types of materials. One is called a strong electrolyte. The other one will be weak electrolyte. These are two electrolytes. And we know that the strong one will produce more number of ions, conductivity will be higher, and weak one will produce less number of ions, so conductivity will be poor. The conductance is due to the flow of ions, as I have told you. Better is the ionic mobility, better will be the conduction. Higher, kitna jaldi move karega, faster the electron moves, better will be the conductance. So the conductivity decreases with the temperature as the temperature increases. Remember, very, very, very important point. The conductivity decreases with temperature increase. Here the conductivity increase with increase in temperature. Okay. The resistance offered by the conductor is due to the vibrating kernels, but here the resistance is due to the interionic attractions. Interionic attractions, suppose there are two ions present and they don't want to get split up already. They just want to be next to each other. So there will be resistance in moving, and if the resistance in moving, there will be lesser conduction. So there are physical changes will take place. Here there will be physical as well as chemical changes will take place. For example, salt in water, fused material, molten, and salts, as all these conditions will provide you the electrical conductions. Now, conduction means there are various formulas to do that. G represent conduction. G is equals to 1 by R. That is, in our physics also we study V is equals to I into R, where V is voltage, I is current, and R is resistance. VIR. So in chemistry, in electrochemistry chapter, G is inverse of resistance. So where G is inverse of resistance, conductance. Also, you should know that G, where R is basically equals to or directly proportional to L divided by A. R is directly proportional to L divided by A. L is the length of the conductor, A is the area of the conductor. In case of metal, it is the length of that wire, area of cross section, But in the case of cell, you will be using this particular cell. Suppose you connect it with some sort of wire or some sort of any kind of battery. There will be this particular length. This is the length, and this will represent area. Clear, everybody? This is the area of cross section. This length of the cube represent L by A. When we remove proportionality, R comes out to be equals to rho L by A. Okay, this A is area of cross section. Now we know G is equals to, when we know R is equals to rho L by A, so G will be equals to reverse of it. So it will be 1 by rho A by L, 1 by rho A by L, and we know 1 by rho is equals to kappa. Therefore, finally, G comes out to be equals to 1 by rho into A by L, and that 1 by rho is equals to kappa A by L. Now, when you multiply this with volume, or with length rather, let's multiply and divide by length. This together, area into length, becomes the volume. And on the bottom you have length. When I fix the length to be one unity, then G is equals to kappa into volume. Kappa into volume divided by L square. Now we need to change something here in this formula to get the conduction values. What are the two conduction values? One is called molar conduction value. As I said, G is equals to K into V, which can be written for molar conductivity purpose. New symbol is used. Molar is equals to what? Kappa into 1000 divided by capital M, where capital M will be the conductivity of 1 mole of the substance dissolved in VmL. Remember, VmL. So VmL of the substance. So this becomes my formula. You should be very well aware of these units also. Similarly, the conductivity of 1 gram equivalent, that represent equals to kappa into volume, which is changed to 1000 divided by N, capital N. N is normality. N is the normality. Are these two formulas clear, everybody? Yes. Can you develop a relation between the equivalence conductance and molar conductance? Yes, that should be equals to N factor multiplied with molar conductance. Yes, that's the condition. That's the relation developed. All right. Okay. We'll see that example which relates the two. This is what I have just told you that. Okay. Let me fix that. Yeah, here. We have it here. And when you take these two, when I divide these two, so what will happen? Will be equals to divide by M. That should be equals to K by K into 1000 divided by N divided by K into 1000 divided by M. K by 1000 cancel, that becomes M divided by N, where M is molarity. We know normality is equals to N factor into molarity. Molarity cancel, and therefore when you cross multiply that molar comes out to be equals to n factor into equivalence. This is the final derivation. Molar, this cancels, and then cross multiplication, equivalence conductance gets multiplied with n factor. That's equals to molar conductance. This is the relation that we have just developed, written over here. Molar conductance is equals to normal equivalent conductance into n factor. Now what happens to the conduction when you actually dissolve in a higher at a higher dilution condition? How does the conduction changes with concentration? There are two comparisons made at this in this particular graph. What is that? Here the concentration is increasing, and here on the left hand side the concentration is decreasing, or we can say dilution is increasing. This gives us one relation, straight line equation, that molar conduction at one particular condition is equals to limited molar conduction minus b root c. This is a straight line that is observed for this equation, for this one, where this infinite represent limiting value, limiting upon dilution, infinite dilution, limiting dilution. So upon infinite dilution, what happens to molar conduction, what happens to equivalence conduction? They become the highest value. Okay, now this is known as Debye-Huckel-Onsager equation. And for weak electrolyte, as the concentration is changing, please notice the graph. For as the concentration is changing, suddenly it shoots up. Suddenly it is shooting up. But for strong electrolyte, it's almost the parallel to what you expect and what you see. But here the change is too much upon dilution. What does it mean? Acetic acid or any weak electrolyte upon dilution starts behaving as a strong electrolyte. You must have studied that in ionic equilibrium also, Oswald dilution law. But here we are not discussing their dilution property. We are discussing what happens upon dilution. We see that their conduction increases tremendously because the number of ions present are very high now. What is Colroche law, everybody? Colroche law represents that the total molar conductance of any salt, for example, I have NaCl, at infinite dilution can be written as of NaCl molar is equals to of Na plus infinite molar of Cl minus. Now it depends upon how many cations, how many anions are present for molar. Suppose I have barium chloride, BaCl2. This is I am giving you for your homework. You need to practice and figure out if you are able to find out that also. Now, but these are the three applications. Let me finish this first. Barium chloride will be equals to, at infinite, barium chloride ka molar conduction will be equals to 1 barium already present and plus 2 times chloride. This is how we represent. Now the application number 1, with the help of the strong electrolytes non-concentration, non-conductance, we can calculate the conductance of weak electrolyte. Weak electrolyte, for example, acetic acid, will dissociate, assumingly will dissociate to produce acetate as well as H plus ion. Suppose I have a salt made up of acetate, sodium acetate, and I have HCl and I have NaCl. They three are going to dissociate 100%. So I will have CH3COO Na dissociating to produce 100% CH3COO minus plus Na plus. Then HCl will dissociate to produce H plus and Cl minus. Then NaCl will dissociate to produce Na plus and Cl minus. But what I am looking for? I am looking for acetic acid to dissociate to produce acetate ion and H plus. With the help of these top 3 equations, I want you to manage to get the fourth one, and you apply their same logics on their on their molar conduction also at infinite dilution. So this I need here, this I need here. So I can write it is equals to acetate is required. So acetate is there in the first one. Then H plus is required. H plus is there in the second one. So I will just take the concentration number 1, 2, these 2, 3, 4, 5, and 6. I want H plus, yes. So concentration number 2 will remain as it is. So HCl will be added. Do you see that HCl is being added here? Yes, because I need H plus in the product side. Now, these are no more present because they are dissociated. They are dissociated. They are dissociated. Don't be worried. So what to do in the left hand side? They are almost, they are nil. They are dissociated 100%. Acetate, is it required? Yes, again in the product side. So first one also should be added. Do you see there is a plus sign here? Yes, plus sign here. And then, do you need Na plus? No. Do you need Cl minus 1? No. So Na plus Cl minus, it should be minus. It should be subtracted. Understood? Understood, everybody? Good job. Now, the degree of dissociation can also be calculated when you divide molar conductance at one particular concentration divided by molar conduction at infinite dilution. Alpha value, remember, always have to be less than 1. So the denominator should be a greater number. Should be a greater number. Now also from chemical equilibrium we know K equilibrium constant is equals to C alpha square divided by 1 minus alpha. Put that alpha here in this equation, you will obtain the K equilibrium in terms of concentration and molar conductance at infinite dilution and at particular concentration. Understood, everybody? These are the three applications of Colrosh law. Okay. Now we need to have the last part of this topic today is cells. Although this is beautifully given in your NCERT and nothing more is required for your board, just give it a quick read from NCERT and follow what I am teaching today. There are two types of cells. One is called primary cell, the other one is called a secondary cell. The primary cells are those which cannot be charged again. They have to be just used and thrown away. They are use and throw. But the secondary ones can be recharged, can be charged. So there are two types of primary cell. One is called dry cell, another one is mercury. There are three types of secondary cell. There are many more, but in your syllabus there are only three: lead storage battery, nickel cadmium, and fuel cell. Let's discuss all of these one by one. In dry cell, you have what you need to know, only that information I have brought to you in this lecture. Anode, what is the material in dry cell? What kind of anode is used? It is zinc. It is made up of zinc. What is the cathode here? Cathode is the graphite which is surrounded by the paste of MnO2. You can take that pencil cell which is present with you. Maybe you are having it in the remote, in the AC remote, TV remote, wherever. This is that pencil cell. If you get a chance, you can open it and see. But be careful, those sharp edges may give you many cuts on your fingers. So be careful when you open. Use a plier. So there will be MnO2 ka paste and ammonium. That reaction would occur. So the question that they ask is, what is the product obtained during the reaction in dry cell? Mn2O3 is the product obtained. And when you open that cell, you might have observed there is some sort of ammonia smell, and that ammonia smell is due to this. Okay. Then what is the electrolyte used? This is very important to note. Electrolyte used here is ammonium chloride and zinc chloride. And what's the E0 cell of this battery? E0 of this cell is approximately in between 1.25 to 1.5. Okay, next. In mercury cell, which are button cells, they are used in the watches, in the wrist watches. They actually have anode again of zinc. The cathode is made up of mercuric oxide, and the product formed is mercury in the liquid form. Dangerous, yes, but it's okay to use. What is the electrolyte used here? It's a combination of ZnO and KOH. And what's the cell potential? It's 1.35 volt. Okay. Then the lead storage battery, I like it so much. Why? I'll tell you. Anode is having lead. Anode is made up of the metallic lead. And that forms a PbSO4 solid, and over a period of time it starts getting accumulated or deposited on the plates. So you need to get it serviced. You need to take those plates out and clear it so that the conduction happens. All right. Now, on the cathode, there is PbO2 which undergoes reduction to form Pb2 plus. Here there is a Pb4 plus present. And you should also notice that H plus is undergoing a consumption. H plus is getting consumed. So question that gets asked in the examination is what happens to the pH of the reaction upon consumption during the discharge of lead storage battery? Does it increase or decrease? The pH increases as the H plus concentration is decreasing, pH increasing. So electrolyte used here is 38% weight by weight H2SO4. I'll tell you one secret. If your lead storage battery, which is generally used in cars is or at homes, is not working, and you give it to the repair person, please fix it. The repair person will ask you, okay sir, you drop it for today, I have to check it tomorrow, I will let you know what is to be done here. So he will not check it, my guarantee. Or he may check it, but he gives you a call at night or sometime that, sir, this is the big problem in your battery, I need to do this and that and this and that. You will be terrified. You'll ask that, okay sir, please replace. How much does it cost? Sir, for others I charge 5,000 rupees. For you, I can manage it to be 4,800. So 200 ka discount I can give you. You'll be happy to hear that. Oh, 200 saved for me. Nice. But actually, what is that person going to do? What is that repair person going to do? He's making fool of yours. How? He's just taking out those plates and removing PbSO4 ka coating. Nothing, no expense at all. Or what is it doing? Just H plus, which is undergoing a usage, is getting consumed. He will just fill it with H2SO4 and ask you to, sir, now it is ready to use for next 5, 4, 5, 7 months, 8 months. You can use it. Give me my 5,000. Mera 5,000 leke aa baba. Samjha? So next time when you go to the market, don't be fool. Okay. Next one is nickel cadmium battery, NiCad cell. The cadmium is used as the anode and nickel oxide is used as the cathode. Electrolyte is just KOH. The fuel cell anode is hydrogen H2 in the presence of basic medium and water forms. And cathode is oxygen in water which undergoes reduction to form hydroxide medium. And the electrolyte used over here is resin which contains NaOH. They are resins used. Resins means just like resins. I'm sure you know what how resins look like. Okay. Now, last part for today is corrosion. Corrosion is a problem that occurs to metals which are electropositive, specifically iron. When you leave it open to air contact, they will get start eating up by the air. When they come in contact with oxygen and moisture, they form a cell on that top of the surface, and then reduction oxidation starts happening. Oxidation generally starts happening, and the corrosion of iron is known as rusting. Now, how to prevent the corrosion? So there are three processes. There are three ways. One is called sacrificial protection by using galvanization process. You can coat that metal with even more electropositive metal so that first that electropositive metal comes in contact with the air and moisture and get sacrificed, and the bottom, the covered one, remains safe. Second one, the cathodic protection or using anti-rust solution. Generally, we paint, we paint so that the contact between the material and air and moisture is cut down to a great extent. That's all for today, guys. I hope your electrochemistry chapter is now completely revised and you are very well ready for your board examination. But all of you, please try all the previous questions available with you from your board and practice NCERT at fingertips. NCERT at fingertips, just to know that you are ready with all the quick questions, quick question answering. So there are all at every most of you might be knowing it. So after every subtopic there are questions given. Do practice on a daily basis. I'm sure you will excel beautifully in your board examination. This is your teacher, Dr. Lakshya Kathuri. I'll see you in the next class, guys. Goodbye. Take care.